Transformations are the same for any function. There are 10 transformations we can apply to functions to make them do different things. Okay, so we're going to be doing this to all of the basic functions, or we have the ability to do this to all of the 12 basic functions that we've learned about, but all of the formulas are the same. We can translate a graph, which means moving it horizontally or vertically, changing its vertex. So left, right, up, down, those are translations. We're sliding it around the graph. If the number we are adding or subtracting is adding or subtracting inside the function, so inside parentheses, inside the square root, inside the absolute value bars, and it's subtracted, we're going to be moving that graph to the right, the number of units that it says. So if you see a -3 in there, it is moving to the right 3 units. If that number, however, is a plus, it's going to be moving to the left. So kind of the opposite way than you would think. Normally, things that go to the right are positive, and normally things that go to the left are negative. But since these transformations are inside, they go the opposite direction. We can also transform graphs, moving them up and down. This is still adding and subtracting. However, it is no longer inside the function. It's going to be outside of the bars, outside of the square root, outside of the parentheses, whatever we're using. If we do -c, yeah, it's down. And if we do plus some number, it's up. Doesn't matter what number or letter is used. I used C on all this paper, but sometimes it's H and K. 2 of the other transformations we can apply to functions. Do these sound familiar, by the way? Are these all things? Okay, great. We can reflect something across the y-axis. That changes the sign of everything because it's a -1 or a negative sign in front of the entire function. Sometimes you'll have to distribute that negative into the entire function. Changes the sign of all of the y values, all of the outputs. You can also reflect it across the y-axis, which means the -1 is inside next to the x. Kind of looks like what we did to check even or odd functions. We're putting a -1 next to x. Changes the sign of the y values. We can also dilate our functions, which is changing the size or the shape of them. If we were thinking about parabolas, it would make it skinnier or wider. Okay, we can do that vertically or horizontally. Vertically, the number is going to be multiplied in the very front, sometimes having to be distributed. If that number in the very front is bigger than 1, so 1, 1.5, 3 halves, 5, 10, 8,000, it's going to be called a vertical stretch by a factor of the same number, c. So visually what happens is it makes the graph narrower. The way I like to remember this, if no one's ever shown you this way to think about it, you know how like on a computer you have like an image and you can click on the image and it has like a top and a side? Okay, if you grab the image and you grab the top of it and you stretch it, is that image going to get narrower or wider? Narrower. That's what's going to happen to a graph. But if you take the top and you shrink it, what's going to happen to the image? It's going to get wider. Your face would get all sorts of wonky and wide. So that's what's going to happen with vertical stretches and shrinks. If that number is between 0 and 1, so like a true proper fraction, 1/2, 1/4, 0.7, that's going to be called a vertical shrink by a factor of the same number. It's going to make the graph wider because we took the top and bottom and we shrunk it down. And then we get to the confusing one. Horizontal stretches and shrinks are all sorts of crazy. This time, because it's horizontal, the number is going to be multiplied inside next to x, like where that negative went to flip it over. If the number is bigger than 0 that you see there, it's called a horizontal shrink, which is backwards. Okay, but it's a horizontal shrink by a factor of its reciprocal, 1/c. And since it's a horizontal shrink, you take the picture horizontally and you shrink it. It's actually going to make the graph narrower, because you took the sides of it and you've shrunk it down. If the number c that you see there in the equation is between 0 and 1, so a proper fraction, it is also a horizontal stretch by a factor of the reciprocal, but that's going to make the graph wider. Because if you grab the horizontal sides of the picture and you stretch it, it's going to make the graph or the picture wider. So we've been using transformations for forever. In Algebra 2, you learned about a function, then you transformed it. Then you learned about a function, then you transformed it. So you know these 10 vocabulary words. What I need us to recognize is the formulas for them, not so much what's happening in a picture. So if you saw f of x minus 5. You need to know immediately, that's shifted to the right 5 units, because that's going to help us do the part of inverse functions where we know if the range changes. We need to know what's happening to all of these graphs. So just a couple of things that I think might be helpful for remembering some of these. To tell the difference between something that's vertical and horizontal, there is some acronyms that are at play here. You might have heard of some of them before. The acronyms are VOS and HIO. Oh. Does that sound familiar? Okay, yeah. So vertical transformations are always outside of the parent function, and they are the same direction as they make sense. So like plus is going to go up, minus is going to go down, big numbers make it big, small numbers make it small. Horizontal is on the inside of the function, and it goes the opposite way than you think. In fact, so much so that next to all of the horizontal stretches and shrinks, we might just want to put the word reciprocal, because not necessarily opposite, but you're using the reciprocal here, which is kind of opposite of the number. So horizontal ones are all the ones that kind of get confusing because they go inside the function, which means to get them out, we'd have to use negative numbers and do the inverse. So they are opposites. VOS, HIO. Vertical, outside, same. Horizontal, inside, opposite. Great. What we need to be able to do, like I said earlier, is look at graphs or look at functions and decide what is happening to them so that we know how they differ from the parent function that we have memorized. How they differ from the v for absolute value, from the little square root, from the sine curve, how they are different depends on these transformations. One of the other things we need to be able to do is write a function for each transformation. You would have done this last year, so this should kind of feel familiar for you. But if we want to write a transformation for each function, we make sure, number one, we do them in the order that are listed, because order matters for some of these, especially if it has the words like then do this, or after that, we have to go in the correct order. So for this problem, we are going to vertically stretch by a factor of 4. We are going to reflect it over the x-axis. We're going to move it to the right, and we're going to move it down. Those are the 4 things we're going to apply to this parent function. What kind of function is this to begin with, though? Quadratic. So we know we're going to take a parabola and we're going to do all of these things to it. We're going to make it narrower, flip it over, move it to the right, move it down. So here's the formula that would do that in the correct order. We have the new function. I'm going to name the new function g of x. And what I would like to do is I want to set up the parabola, set up the, what is this called? Quadratic. Wow, I just lost that word in my head. With some space to put things places. Parentheses, creating an inside to this function. What? Focus. Okay. To vertically stretch something by a factor of 4, you're going to put a 4 in the very front. If I had something to multiply it to, if this was already a more complicated equation, I'd have to distribute that 4. There's nothing to distribute it to. I want to reflect it over the x-axis, which means I'm going to put a negative right here. If there was something to distribute it to, I would have to distribute. There's not for this problem. I want to move it to the right 4. Well, that's subtracting numbers on the inside, so I'm going to put a minus 4 on the inside there. And if I want to move it down 2, that's at the back, down 2. If there was anything to simplify on each one of those steps, I'd have to. This came from the parent function, so there really wasn't much I had to simplify each time, but I made sure I did it in the correct order, just in case. Do you see how you just take each of the 4 things at once and you put them in the equation? Yes. Okay, I want you guys to try both B and C, and well, probably after lunch, huh? Because it's about time to go to lunch. I forget because we don't have the bells. So after lunch, when y'all come back, we will be doing B and C. Okay, if I were going to do B, since you had some time to think about it, again, order matters, and if there's anything to distribute, you would have to. The order that this is written is also one where you wouldn't really have to distribute anything. So we know we're starting with the parent function of a horizontal stretch. Starting with the parent function of a square root. And we're going to horizontally stretch it by a factor of 3, but I'm not going to use the number 3. I'm going to use its reciprocal. That would be 1/3. It's the ugliest looking 1/3 I've ever written. Next to the x. I also want to reflect that over the y-axis, which means that's really negative 1/3 next to the x. I want to move it to the left 1. Left is a horizontal direction, so that number also goes inside. And then we make sure that it's actually outside of the square root to move it up, plus 7. It's outside of the parent function. The parent function ends right here because the the bar stops there. The absolute, or what is this called? I'm losing all my minds. Square root. The radical ends right here. So the plus 7's behind it. Questions about that? Does that look familiar, like things we've done before? For the second or the third one, part C, what kind of function is it starting with? Absolute value, so this would be a V on a graph. If we were writing this one, a horizontal shrink by a factor of 1/2, that is a horizontal dilation, which means I'm going to use the reciprocal number here. And then we also want to move it to the right and then up. Okay, so if I have my bars and a horizontal shrink, leave some room there. I use the reciprocal. It's going to be multiplied in front of the x. To move to the right, I'm subtracting the opposite direction than normal for addition, or for positive things, and then plus 4 for up. How do we feel? Do you see how each of the little instructions corresponds to a place you either multiply or add numbers for these graphs? Great. Let's keep going. We're going to work the opposite way on the back of this. And this time I've given you the equations, and you're just going to identify what we did for them. I like going from start to finish, so what I'm going to do is I'm going to look at this parent function. What kind of parent function is this? Ooh, why is it quadratic?
Oh, there's a square.
There's a square. So this is a quadratic because it's squared. So we know that we are comparing this function to the normal parent function, f of x equal x squared. Everything that's different compared to the boring x squared version, every number that's put in there is a transformation. We've got the negative, we've got a 3, we've got a minus 2 on the inside, and we've got a plus 4 on the outside. Each one of those things corresponds to a different transformation. Putting negatives in front of functions is going to reflect it over which axis? The x-axis. So this is going to be a sad parabola. That number 3 is multiplied in the very front. Numbers that are multiplied in front, I know it's outside so it's vertical, but since it's 3, is that a stretch or a shrink? Stretch. That's a vertical stretch. I'm okay with shortening vertical and horizontal to V and H respectively. Vertical stretch by a factor of 3. So it's going to get narrower. And we're going to move its vertex, or its starting point, both to the right and up. So this is going to be a horizontal translation, H translation. To the right, I'm okay with arrows, to the right 2 units. And a vertical translation, up 4. Those are the different transformations that we applied to the boring parent function to make the parabola that would show up in A. It's a sad parabola that's stretched with its vertex moved to the right and up. That's all of those things I can tell just from looking at this. And that's important for us because when we're doing the kind of things we're doing with functions, we need to know its domain and range right away. So we need to know how it's changed from the normal parent function, moving up, down, left, right, getting skinnier, wider, all that sort of stuff, flipping over. Can you guys do B and C for this kind of example as well? Just kind of working backwards, the opposite direction. What type of function is question B? A square root. So we know we're comparing it to the normal square root function, square root of x. So there are 3 differences. There's a negative in front of x. We're having a plus 3 inside the square root underneath the radicand, and a negative 2 on the outside. All 3 of those things translate to different transformations. The negative on the inside is also a reflection over which axis? Over the y. This is going to reverse directions. Instead of going this direction, that square root function is going to go that direction, flipped over. And it has 2 translations. It's going to move horizontally, so horizontal translation. Which direction? To the left. And then vertically, how is it going to move? Down, yeah. So we would know just by looking at this one, so that we could do a problem with this kind of function. If we were to just sketch it real fast, we know it's moved 3 units this way and 2 units down, so it's got an origin point right there at vertex. And instead of normally, the square root function goes this way, but since we're reflecting it over the y, we know it's going to go that way. So all of this stuff we're able to use as a precursor to some of the things we've been doing in class and recognizing those domains and ranges a little bit quicker. Now the third type of function here, we haven't really talked about. It's not one of the 12 basic that we learned about, but it is a pretty basic function. Does anyone know what that one's called? Cube root, yeah. Cube root function. Its normal is just like the square root function, except it's a different root. So it's normally looking like this. Cube root of x. Yes?
Like, what does it look like on the graph?
A cube root function normally looks like this. And that's not logistic, so that's not bounded between 0 and 1. Its range actually goes from negative infinity to infinity, just very slowly. So imagine this kind of looks like a square root, but it's reflected, and it's not technically the same points as a square root, but it kind of is like both parts of it. Remember, cube looks like this, so cube root is the inverse of it. So it's just the reflected version of a cube function.
Well, if it's like a 4 instead of a 3 or anything higher.
That would be a fourth root. I don't know off the top of my head what a fourth root looks like. It's not common enough for me to know that, but I can Google it if you care. Or a fifth root. I don't know what those look like off the top of my head. That was a great question. There are 2 differences for the cube root function here. We have a negative in the front, and we have this 7 inside, multiplied by the x. So the negatives in the very front are always going to be, negatives are always some sort of reflection. And since this one is outside of the square root, it's going to be over the x-axis. So we know the shape that I've kind of sketched up there, not this one, that's the cube root, or that's the cube function. It's going to flip over. We also know that because that 7's in there, it's going to be a horizontal what? Stretch or shrink? Shrink by a factor of its reciprocal, 1/7. So we would take it horizontally and shrink it while flipping it over. So it would look something, here's a bad sketch of it. Something that's terrible. I tried to shrink it, but it's hard to do. It's hard to do that without actual coordinate points. So you would take the sides of it and shrink it, which means you're pushing them inwards, so it would get narrower. And it would flip over since we reflected it over the y-axis. That's really a bad graph. Please don't look at that for too long. We can graph it in our calculators if we really wanted to see what it looks like instead of my bad sketch right there. Okay, so we can look at the equations and decide what's changed comparing it to the parent function. But we're not always going to be comparing it to the parent function. Sometimes we're going to compare functions to other already transformed functions. So in example A, what type of function am I dealing with? A square root. And in F, the square root function has been translated which direction? To the left 5 units. All of a sudden, we now have the G function where the graph had been translated from the parent function 2 units to the right. But that's not where we started. So if we think about this one, a quick sketch of this would show us that we started off here with a square root function that looks something like that. And we ended up here with a square root function that kind of looks like that. So what transformation did I apply from F to get to G? How many units did it actually move? 7. So to answer this question, you would say that this wasn't a horizontal transformation to the right 2. You would say it's a horizontal translation to the right 7. Because that's how many it took to go from where I started with f of x to where I finished g of x. So sometimes we're not comparing it to the normal parent function. We're comparing it from one to another. This is why sketching them very quickly with these simple transformations is helpful to see a difference. Okay, for part B, f of x is translated where? 2 units to the right. And then all of a sudden g of x is what? 5 units to the, that way. What is that way? Oh my gosh, I forgot the word left. Left. Oh my goodness. So we went from something that looked like this to something that looked like this. How did our transformation, or what transformation did we apply to it? How many to the left? Mm-hmm. Okay. You guys have C. A nice little challenge there for you. How did I get from F to G? If you need the sketch, you can sketch it. Actually, it's a challenge. Try sketching both of them so we can compare them. Okay, so the first one, the F function, had already, compared to the parent function, had been translated down 3 units, so it would look something like this. And then g of x was translated up compared to the parent function. But comparing them to each other, how do we get from F to G? 7 which way? We went up. How many? 7. You just answered that question and I forgot. So again, sometimes we're not comparing them to the parent function. Sometimes we're comparing them to other already transformed functions. Not a big deal if you can handle what the already transformed function looks like, compare it to the one that you want to know, and then go from there. Okay, last kind of question we're going to do is a describe and graph each transformation. Yes, I know we could plug this into a calculator, get a table of x and y values, plot them, and then play connect the dots, but that's lame. We're going to do it like this. We're going to graph the parent function and then look at the transformations that we should apply to that parent function and to be able to do that by hand quickly without having to get a table of inputs and outputs. So first things first, what kind of function is letter A? Quadratic. So quadratic parent function is f of x equal x squared. So we know an x squared is a parabola. It has coordinate points that start at the origin. So we're going to go ahead and put a little dot at the origin. And we're just going to do a few points. If I jump 1 to the right, I have 1. What's the square of 1? What's the square of 2? 4. What's the square of 3? 9. Okay, if I reflect those across the axis of symmetry, I know I have these coordinate points for the parabola, aka a nice looking U. And I'm going to connect those dots with a dashed line so I know that that's the parent function. That's where we would normally start graphing a quadratic. However, we have 4 transformations we've applied to this normal quadratic. What are those 4? What is this one? A reflection over the x. Now what that means is we're going to have a sad parabola. So whatever we get as an output, we're going to use the negative version of it. What does this 2 mean? Vertical stretch by a factor of, so every output I get, I'm going to multiply it by 2 to make my graph narrower. I then move the vertex a little bit. This minus 2 that I see inside the parentheses is going to do what? We're going to horizontally translate it, yes, to the right 2 units. And last but not least, we're going to vertically translate it up 3 units. So I could take every single one of those coordinate points and do that. But what I find easier is to use the same pattern we use to graph the parent function and just apply these things to it. Now, those horizontal translations and stuff, this is going to affect the vertex of my graph. My vertex is actually going to be at 2, 3 because I'm moving it to the right and up. So I already know that I have a coordinate point here. Let me use a different color. 3. 2, 3. There's where the vertex of my graph is going to be because it went over 2 and up 3. Okay, now every time I get an output, I'm going to use the reflected version of it and multiply it by 2. That's all this stuff right here. So if I jump over 1, I normally square 1. What's the square of 1? 1, but use the negative version of it and multiply it by 2. Let me do that again. So I jump over 1, that's 1 is the input. Not 3 because I'm just going from here. Over 1, square of 1 is 1. But I'm going to use the reflection of it, which means instead of going up 1, I'm going to go down 1. And I'm going to multiply it by that scalar by 2. So actually my next coordinate point is here. If I jumped over 2 spots, the square of 2 is 4, but make it negative. So I'm going to go down 4. 1, 2, 3, 4. But multiply that by 2. 5, 6, 7, 8. This is where my next dot would be because I'm stretching it further. Here, I'll scoot it down. So normally it's 2, 4, but we're doing 2, multiply by negative 2, negative 8.
Is the first one on 2, 3?
It is on 3, 1. Oh, the vertex is on 2, 3, yes. Sorry. Now I would run out of space if I were going to try to keep playing connect the dots. So I'm going to reflect those coordinate points across the axis of symmetry so that I have created a stretched graph. We have reflected it, we have made it narrower, and we have moved the vertex to 2, 3. But I want you to try it this way just one more go. We will graph it together, but I want you to identify all of the transformations for part B for me. So tell me what type of function it is and identify all the things we're going to do to that function, and we will graph it together. Okay, now that we've identified the transformations going on here, we need to apply those transformations to the parent function. So what does the square root parent function look like? Now we know it looks like this because you answered that on the quiz trade cards, but don't do that. Let's make it accurate. To take the square root of something, we're just going to pick numbers that have easy square roots. What is the square root of 1? 1. Okay, so I have the coordinate 1, 1. 3 does not have an easy square root, but 4 does. What is the square root of 4? 2. I'm going to plot that point. 5, not an easy square root. 6, no. 7, no. 8, no. 9, yeah. What's the square root of 9? 3. So there's my 3 coordinate points that I'm going to play connect the dots with that fit on this graph. There's the parent function. That's truly what the parent function for square root looks like because we're square rooting all of the input numbers. But when we are graphing the one we want, we are still going to change the vertex here. We only are moving the vertex to the side. We're not moving it up and down, so it's still comma 0. But this is going to be negative 4, 0. So my first coordinate point is at negative 4, 0. I also know that the only other thing I'm doing is flipping the coordinate point across the y-axis, which means instead of going up and to the right, like this is going to go, I'm going to go up in which direction? To the left. But the same pattern applies. So go over 1, up 1, over 4, up 2, and so on and so forth. All we have done is reflect it, flipped it over, and then scooted it to the left. Again, if this is not clicking for you going from the parent function and applying the transformations in your brain, you do have graphing tools to be able to do it. So there's plenty of ways you can do this.